Hi everyone, we're just going to wait a few moments to let a few more people come in and then we'll start the webinar. Hello and welcome to the Institute for Molecular Science and Engineering's webinar, Green Light at the End of the Tunnel, Breakthrough into 3D Printing Using Green Light, presented today by Dr. Ali Mohammed from the Dyson School of Design Engineering at Imperial College London. This webinar is part of the IMSE Seed Funding 2022 Projects to Solve Grand Challenges webinar series, which highlights all of the amazing projects that are being funded in this round of IMSE Seed Funding. The theme of this year's seed funding was sustainability and circular economy. I'm Leah Adamson and I'm the Events and Communications Manager at IMSE. So I'm going to be putting some helpful links in the chat today. These are links to the IMSE Eventbrite page where you can find registration for all our upcoming events, including our annual lecture this year. The IMSE YouTube channel where all our previous webinars are uploaded, and this one will be later. Our IMSE blog, the Never Lit the Spoon podcast, all of our previous briefing papers, and registration to our IMSE newsletter. So just a few top tips to make sure that we have a really good webinar. If you wish to ask a question, please put your question into the Q&A function, and you can do this at any point during the webinar. You don't have to wait till the end. So your questions will be answered at the end. Please do not put questions into the chat function. If you have any technical difficulties, please message IMSE Imperial privately into the chat function, and a member of the IMSE staff will help you. So I'll now hand over and introduce our presenter for today. Dr. Ali Mohammed is a research associate at the Dyson School of Design Engineering and part of the Advanced Manufacturing Group at Imperial College London, working under Dr. Conor Myant. Ali completed his bachelor's in chemical engineering at UCL in 2009, after which he worked as a process technologist for 3 years at the Royal Dutch Shell's largest gas-to-liquid plant to date. There he helped successfully and safely commission the plant to see through to its first production of GTL fuel. He was awarded a Special Recognition Award by Shell in 2010 for his efforts. In 2013, he completed his MSc in Biomedical Engineering at Imperial College, with a project supervised by Professor Julian Jones in his Biomaterials group. He continued on to his PhD in the Jones group and graduated in 2018. His research was based on advanced nanocomposite double network of hydrogels for cartridge repair. Upon graduation, he was awarded the Larry Hench Prize for Excellence in Biomaterials Research. During his PhD, Ali also completed an associate degree at Harvard Medical School, where he focused on cancer biology therapeutics. He has research experience in tissue engineering and biomaterial synthesis, polymer chemistry, cancer biology, and additive manufacturing. His research interests include novel materials and enhancing 3D printing technologies. So thank you, Ali, for the presentation today, and we look forward to hearing what you have to say.
Great. Right, thank you, Leah, for the introduction. Hi, everyone. Thank you for tuning in. So today, my talk is going to be about green light at the end of the tunnel, a breakthrough in 3D printing using green light, and it's part of the seed funding webinars by IMSE. So briefly, the contents through this lecture will be history of additive manufacturing, some information about light-based printing, bioprinting, algae and bioprinting, the IMSE project that myself and the team are working on, some pilot work, the experimental design going into the IMSE project, summary, and then we'll have a Q&A. So the history of additive manufacturing. So it all started in 1980 by Hideo Kodama, who filed the first 3D printing patent idea. Unfortunately for Kodama, this idea was never commercialized, and this was very sad as it could have started his legacy into 3D printing. The reason behind this is he ran out of money, as a lot of, research groups do. However, in 1984, stereolithography was created by Chuck Hull, also known as SLA. And 2 years later, Hull was granted the first patent into printing for SLA. He went on to co-found 3D Systems. A lot of you that know 3D printers and The manufacturers will know that 3D Systems is one of the biggest companies around. In 1987, Descartes filed for the first patent for SLS, which is selective laser sintering with DTM. However, this was later acquired by 3D Systems, who was essentially acquiring a lot of the new technologies coming to the market. In 1988, 3D Systems sells its first commercial printer for $300,000. That's the SLA1. $300,000 is the equivalent to about $1 million now. These printers actually go for about $3,000 to $5,000 themselves, so you can see how times have changed. In 1989, Crump files for a patent for FDM, which is fused deposition modeling, one of the most popular types of 3D printing technologies. And he went on to co-found Stratasys, which is another major company in 3D printing. In 1997, the first 3D printed metal process using laser additive manufacturing, so known as LAM, was created. And this uses high power lasers to fuse together titanium alloys. So in 1999, the first 3D printed organ transplant was created. This was a lab-grown urinary bladder at Wake Forest. And in 2005, riprap was invented. This was an important turn in 2005, as it was an open source concept to create self-replicating 3D printers, 3D printing processes. And this really opened the door for the creation of new 3D printers. And in 2008, the first concept under 3D riprap was created, which was called Darwin. In 2009, another important time for 3D printers was when the FDM patent expired by Stratasys. This meant that a massive influx of supply of FDMs came to the market, dropping the price from $10,000 to $3,000, allowing home users and regular people to use it rather than just people in the lab and companies. In 2012, B9 and Form 1 created their DLP and affordable SLA machines. This was, again, a very important step, and many lab users will recognize the Formlabs printers as well as the B9 creators. And in 2012, we'll come to this later in the webinar, Anthony Atala's famous TED Talk on bioprinted kidneys. This was a major TED Talk that basically brought bioprinting into the world of the news, and everyone was talking about it in 2012. In 2013, the first 3D printed robotic human heart was produced, and in 2015, CellLink, the Swedish company, made their first commercial bioinks for printing cartilage. So from 2019 to now, a lot of expired patents have come to light, which meant a lot more companies are able to produce printers and utilize the expired patents. This meant a lot more companies are being made, a lot more competition for 3D systems and Stratasys, which is good as it brings the prices down for these 3D printers. So there's a growing variety of printing technologies, as we kind of saw. And the global 3D printing market size was $13 billion in 2021, and this is expected to grow by 20% in 2022 to 2030. Globally, 2.2 million units of 3D printers were shipped in 2021, and they're expected to reach 21.5 million by 2030. So essentially, a lot of people across the world are going to start owning 3D printers. So this aggressive research and development in 3D printing and growing demand for prototyping comes from various industries, and this includes healthcare, automotive, and aerospace and defense, and they're expected to fuel the growth of the market. So as you can see highlighted there in red, others, and under others comes bioprinting, amongst other developing technologies, and that accounts for nearly over a third of the technologies being used by 2030. So two of the most common light-based printers are DLP and stereolithography, digital light process, and SLA. So an SLA is a laser-based stereolithography technique. A UV laser essentially cures the resin in the tank to form the object point by point. So you can imagine it's essentially a laser that colors in every layer, and the platform moves up, and the pinpoint laser colors in the second layer. And this is one of the most highly precise 3D printing techniques available. On the other hand, you have the DLP, which is the digital light processing printer, which runs on LEDs rather than lasers. The resin is secured by a light projector, one whole layer at a time. The light shines a specific shape depending on the layer. The DLP printers use a light projector. The layer's shape is defined by reflecting lights with mirrors. So a DLP's resolution depends on its projector and how many pixels or voxels are available. For example, a full HD projector usually has 1080 pixels. So a 3D printer with a large build volume has a fixed number of pixels, making it impossible to 3D print small details when building at full scale or larger scales. The projector used by the DLP printer is less expensive, however, and this allows them to be cheaper printers than SLAs. A very similar concept to DLP printing is LCD, which is liquid crystal displays. Again, this usually runs on LEDs. However, there's a slight difference. It has an array of LED lights that shine through an LCD screen, which absorbs quite a lot of the energy, up to 98%. However, the LCD screen acts as a mask or a stencil between the LED and the bottom of the resin tank, only letting in through specific shapes. This is where the LCD and the DLPs differ. LCDs are also called masked SLA. And since the LCD screens are also inexpensive, this technology has made resin 3D printing more affordable than before, and you can buy some of these DLPs and LCD printers for a couple of £100. In most cases, DLP and LCDs are quite interchangeable. So some advantages of stereolithography. The relatively fast production. It's a nozzle-free process. You can handle complex models. Scalability is simple. No wasted materials, as you can recycle your resins. And it allows you for a wide range of potential materials as the polymer chemistry and the production of new resins develops. Some disadvantages, however, it requires post-curing. Raw material can be toxic, and it's a relatively more expensive process due to the printer and the resins. Limited to photosensitive resins, and the resins do expire. Even though you can recycle them, they have photoinitiators which can be consumed by oxygen and over time can be depleted. And also you never get a smooth finish at the micro layer because you get a stair step rather than a smooth finish. And very importantly here to highlight, high intensity UV light is not suitable for in-situ cellular prints as it damages the DNA. The laser uses a 405 nm light, which is not suitable for bioprinting. Very similar advantages to the SLA for the LCD and DLP printers. However, as you shine an entire layer, it's actually a faster print than the SLA, which is a huge advantage if you're looking to speed up the prints. And the disadvantages are very similar to the SLA system, as mentioned. However, we are also more limited by the resolution here, as if when you scale up, the pixels can't catch up to the size, so you get a limited resolution in the prints. And again, although this is a lower intensity UV light due to the less energy being used, it's still toxic to cells because an SLA process is very quick. However, a DLP might shine its light for a longer time per layer and can also cause damage to the cells if you're trying to print in situ. So quickly to summarize, limited to cell seeding after the print is complete. So you can create your scaffolds for bioengineering, tissue engineering applications, but you have to put your cells in after. A way around this is to create a bioprinting technology that can print in situ. So what is bioprinting? It's essentially in situ printing with cells and biomaterials instead of the traditional metals or plastics to create 3D constructs with similar functionality to the native tissue. So the first bioprinter was technically developed by Thomas Bolland and co. in 2003, where he created a bio-ink. And it was a very simple process where they simply deposited cells into a culture dish of collagen. And they created a few layers, and that was the start of bioprinting. So bioprinting technologies. Since then, bioprinting has developed, and these are the three main types of bioprinters. So you have the inkjet bioprinter, which has thermal and piezoelectric units, micro-extrusion bioprinters, which operates on pneumatic, piston, and screw control, and laser-assisted bioprinters, which has a mask. So the limitations of inkjet bioprinting, they have low viscosity and limited mechanical properties. The bio-ink must gel and solidify as the layers go through, and you have very low cell densities as it can't handle higher ones. This is normally used for skin grafts. The most popular type is pneumatic and piston through micro-extrusion. However, some limitations to this is lower cell viability due to the shear stresses, lower resolutions due to the gauge size, and slower print speeds. Some advantages are you can have larger prints, which are more like organs. You have multiple materials. You've got multi-nozzle and coaxial mixing, so you can have a more complex material. Low to high viscosity bio-inks can be used, and gels that are already set. Some limitations of laser-assisted bioprinting is it's a very low print speed, high material and cell wastage as you only deposit a small amount from a large vat, and it cannot print multiple layers very easily. So this is really just limited to precise cell placement. So there is a difference between bio-inks and biomaterial inks, and to walk you through it very quickly, a bio-ink consists of cells within the ink. However, a biomaterial ink essentially is a material that is printed and then the cells are put onto the material after the print is completed. So a bio-ink is the true definition of what bioprinting is. And bio-inks normally consist of hydrogels or polymer matrix, cells, including stem cells or bone cells, cancer cells, etc., growth factors, nutrients, drugs, antibiotics, and microcarriers. So your bio-ink can be quite elaborate. So, as mentioned, Anthony Atala's TED Talk about a 3D printed kidney. So in 2012, Anthony Atala's famous and brilliant TED Talk showcased a bioprinted transplantable kidney using live cells, and this brought mass attention to bioprinting. However, the print was non-functional, and it had one cell type, and it lacked sufficient vascularization. And it had to be kept in a bioreactor to keep the microenvironmental parameters, such as temperature, pH, nutrient, and gas concentrations constant. And it needed consistent mechanical simulation to keep it alive. This means that it can't be mass-produced universally, as it requires individualized customization, as the process is very slow and long. And a point about vascularization is that because it was printed using a nozzle extrusion, the vascular structure was very, very limited and did not reflect the actual vascularization you get in real tissue. This is Anthony holding the 3D printed kidney. And I really like this image as it's quite an iconic image showing the first major reveal to the public. And you can also see that Anthony might have been a bit nervous because his hands must have been clammy as he couldn't get the gloves on properly. And everyone in the lab can probably relate to this. So algae and bioprinting. So bioprinting is a very versatile technology that can be used across different species and living organisms with a wide range of applications. And this can go from pharmaceuticals, food production, renewable energy. So it's not really limited to mammalian cells. It can also be used for bacteria, microbes, fungi, and algae. So what is algae? It's a group of predominantly aquatic photosynthetic organisms which lack their true roots that plants have and stems and leaves, but has a specialized multicellular reproductive structure similar to plants. So you've very likely come across algae in lakes or ponds, canals or rivers. It's normally just a green blob or mass on the surface, which you would have probably ignored. So some studies that have already looked into 3D printing with algae include the study which looked at the co-cultivation of microorganisms in close contact with microalgae, and this was to improve the oxygen supply of different cell types by photosynthetic oxygen evolution. This was achieved by bioprinting immobilized microalgae embedded in hydrogels and subjected the plants to either direct continuous light or light-dark cycles. They measured their sustainability and their viability through flow cytometry and fluorescence imaging. But the point here is, as you can see, the resolution of the print is very, very limited, and it's a few millimeters in height, and the spacing is quite basic. So it's a very, very simple printing process where it's just a grid. A little bit of a more elaborate study here. It shows the work, shows the ability of human cells and algae to survive in the same print. but the structure is again limited to grids. And although the print size might be relevant, as it's stated in the study, for biomedical applications, the mechanical structural integrity of the design and the design complexity are very limited. Again, you can see that it's a grid-like structure. And finally, we have a look at another study, which uses an alginate-based hydrogel, and it studies the chlorophyll content and the photosynthetic rates of microalgae printed in a grid-like structure under constant illumination. Again, the 3D print was limited to a basic grid structure that is a few millimeters high. So as you go through the research and find bioprinting with with algae or other microorganisms, you find that the main limitation is the design complexity and the ability to print very complex structures. So what can the next step be? Green light. So bioprinting is limited due to the nozzle size and bioink viscosity, which results in the low resolution of the grids that we've seen, which results in basic models with limited design complexity. So you can never truly replicate organs or tissues if you're printing with such limitations. The shear stresses and extrusion pressures also result in cell death. If you were to use a DLP and SLA, they will not be viable as they have high UV intensities at wavelengths that are toxic to cells. So prolonged exposure in the near visible light spectrum, 380 to 410, and slightly higher are carcinogenic and initiates cell apoptosis. So all visible wavelengths of light can be toxic to cells in vitro, depending on the dose and the wavelength, with the more energetic, shorter wavelength of light below 500 nm particularly being detrimental. However, while cells stand intensities of above around 1 kilowatt per centimeter cubed at 614 nanometers for several minutes, the maximum dose is 405 is only 100 to 200 milliwatts per centimeter squared. So you are really limited by how long you can expose them. In contrast, green light has a lower energy and is less harmful to cells and DNA. So green light, which we chose at 510 nm, is a very viable option for bioprinting using light. And based on literature, our intensity has been set in our work to 120 milliwatts per centimeter squared, much lower than expected harmful levels. So these orders of magnitude are also lower than the visible light experienced outdoors when you're walking in the park or when you're out swimming. And that is also important as algae is always out exposed to light. So green light can provide an answer to higher resolution in-situ printing using common and cheap technologies, which takes us to our IMSE Fund team. So that's Dr. Connor Mind. He's the lead of the Advanced Manufacturing Group at Dyson, and that's Dr. Laura Barter, the director of the Agri Futures Lab in the Department of Chemistry and part of the MSRH in Hammersmith. And Photocentric, which are our industrial partners. We've worked with them on several occasions to test new photoresins and test out their material properties. So together we're working on this project. So it's a very collaborative effort. On the design engineering side, with us, we look at the material development, the process, CAD development. And in chemistry, we look at the biological studies, the expertise in algae growth and analysis, and Photocentric have provided us with the DLP and the printing equipment, machines and resin expertise. So altogether, we're hoping to push this new technology forward. So some of the aims for this project, we're looking to provide a series of 3D printed hydrogels with high resolutions and complex structures using the g-DLP. So this is a proof of concept green light bioprinting study. Ultimately, we're looking to get an algae-infused photoresin, which is the first of its kind. So we are looking to study the cell survival of algae within the photoresin components separately. And this will allow us to look at the windows that we can use for each component within the photoresin. And that will result in the generation of a biocompatible algae-infused photoresin. Moving from there, we're going to be looking to 3D print the hydrogels with varying design complexities using the algae resins. ultimately, one of our main aims as well on the biology side is to submerge these prints in tap media, which is a common media used with algae, and assess the printed algae for photosynthetic rates, cell density, and viability, essentially to see how much do they thrive and how much do they survive. Okay, so here's some of the setup. That's our printer. That's the printer with the backlight on, and some images of the actual layers beginning to print, just for examples. Here you can see the DLP intensity, which is 60 milliwatts, and ours is around 110. So this is an ultra high resolution LCD panel printer. The Z layer can go down to 25 microns, and the XY resolution is 47 microns, which is higher and more accurate than most SLA printers on the market. So some pilot work. So the g-DLP photoresin development. So Dr. Olivia Kawasaka was a PhD student in our lab, and she put in a lot of effort to help pilot the work for the first g-DLP photoresins and prints, which we'll see in the next few slides. So Olivia created this workflow for optimizing a photoresin using light-based printing. In her process, she looks at optimizing for photoinitiator combinations and concentrations, the number of bottom layers that you need to attach to the build platform, exposure time for the bottom layers, and exposure time for consecutive layers. And it's quite a complex system that you have to have with error and trial and error, sorry. So more of the pilot work, components of a green photoresin. You can use synthetic polymers, which have minimal batch-to-batch variation, more chemistry options. Mechanical properties can really range, and they can be photo-curable. The price can range from very expensive to very cheap, so there's advantages and disadvantages there. A lot of the synthetic polymers are hazardous in their monomer state. However, some aren't. So some examples are acrylic acid, acrylate-based monomers, isopropyl acrylamide, also known as NIPAM. Natural polymers, often derived from plants, they have low variation in batches. They're cell cytocompatible. They do lack cell binding sites. They are cheap. They're, however, non-photocurable, so they do need modifications on their end groups to make them photocurable. Their mechanical properties can often range. Some examples that are common are alginate, agar, cellulose. So when printing with a green light printer, you have to find the right wavelength for a photoinitiating system. All of this combined, we have monomers and cross-linkers that are mixed into a complex photoinitiator system with 3 different components, and then additives that can be media, can be biomarkers that increase the cellular attachment, or just have softening effect or a stiffening effect in the material. So first g-DLP photoresin development. The initial steps were to do spot tests, and these spot tests consist of a array of different light exposures on the same build. So here we try to see what is the minimum light exposure we need to get a certain gel from our resins. So this is very important, as this gives us the starting point for the exposure that we're going to need per layer. And every time we get a failed attempt, we increase the photoinitiator or increase different concentrations within the resin. And here you can see that we had a successful batch, and here you can see that we didn't, and that was during photoinitiator optimization. Once we got to the point where we were very happy with what we had, as in a photoresin that solidified and gave us a gel, we moved forward and we optimized it a little bit further and tested the photoresin properties. Here we look at the viscosities. So we wanted to ensure the resin isn't too viscous, and that will cause suction and adhesion on the build platform and printing. And as we're aiming for very soft gels, this will just peel them off, and it'll cause failure of the print when the layers are lifting. We also studied the contact angle of the photoresin on PDMS and FEP film. FEP film is what is used in the tanks of DLPs and LCD printers. We wanted to ensure there's an even distribution when the resin came to us, a low amount or low volume, so that it spreads rather than clumps together. So this is essentially the setup. It's a scheme showing the setup of our printer where we add the photoresin to a resin tank, and the green light goes through the LCD screen, and you get the 3D printed scaffolds here, or the 3D printed cubes. So the next step was to attempt and 3D print using our 3D printer, g-DLP. So we designed some basic 1 centimeter cube structures with a solid block, a single channel, and a 7-strut 2.5 millimeter lattice, and attempted to print using that base formulation that we generated. So the first attempts weren't very successful. We would only get 1 slice of the structure on the print platform, and the rest would fail. So we optimized for light exposure during the bottom layers. So the bottom layers are the ones that have to really attach to the build platform. We saw some success there. However, the print continued to fail. So we optimized for cross-linker concentrations to give it a bit of a boost, so that the material was a little bit more solid. As you can see there, it's quite gel-like. We reached a very good point where the structures were 90 or 80% successful. However, we saw that a lot of it was failing. So we optimized the photoinitiator concentration and the normal layer exposure durations, which finally resulted in the first successful green light printed structures. So we have a photoresin that's an optimal condition with specific optimal light exposure setup for that resin. And as you can see here, a comparison between the CAD designs and the 3D prints. They're very, very similar. Next, this is some work Livia was also doing. Once we had the formulation that was working, she looked into creating this study where you find the minimal channel size that you could physically print with the setup and with the printer, as well as the resin. Here you can see that we at 40 seconds we had under curing, at 80 seconds we had over curing, at 60 seconds was the sweet spot where we basically had the measured, which is the black dots, were very similar to the intended, which are the red dots. And we actually got to 300 micron channels. So we can print complex structures with 300 micron channels. So moving forward from there, we were able to print highly accurate models of an 8-unit lattice with 1 millimeter diameters that were completely hollow. With the same hydrogel on both the DLP and SLA, this was not possible. So using UV light, this wouldn't work on the regular printers. This could not be achieved using the same resolution as the gel was too soft, and the materials were not performing the same way as they did on the g-DLP. So to further test our capability, we actually, instead of taking the entire lattice over here, we took 1 unit lattice. So this print is actually a quarter of the size of this entire one. So this is actually 5 millimeters tall and wide, and the entire lattice structure is visible. And we can push these channels to 300 microns instead of 1,000 microns at the moment over here. So using some ISO standards from ASTM, we were also able to run some tests to see how accurate and how successful our materials can be at their soft state during the 3D printing process. And we saw that we can get up to above 95% accuracy on these prints. Next, we looked at the swelling behavior of our multi-component gels. So we could actually modulate the swelling behavior of our gels based on the lattice or whole or solid structures, or we can play around with the chemical components, modifying them to get either less swellability or higher swellability post-printing. It's good to mention here that the actual size of the gel when it swells doesn't change very much at all. I think the increase was between 5 to 8% increase in size at the swollen state. So you don't get much deformation in your prints. Next, we looked at the material characterization of the mechanical properties. So here, as you can see, when we go from solid to lattice, you get lower compressive stress at failure. However, the deformation increases, and this makes sense because with a lattice, you obviously have more air, more space. So the material is essentially softer without intrinsically being softer. So that means it can handle a higher compression before failing. Imaging, so here you can see an SEM that we did just to measure the layers and to see if there's any delamination in the print between layers. Delamination would occur like this, but then again, during SEM, you have to freeze dry it. So that could be caused by the freeze drying process. So using an optical microscope, we had a look at the layers and they're within above 95% accuracy of the layer that was intended by the design. So by design, it's 50 microns that we chose per height. And here you can see that it was around 50 microns. It's very difficult to see without an arrow around it, but it's very, very accurate. So next, so part of the pilot work was to look at the Photoresin Cytotoxicity. So Dr. Alessandra Pina was kind enough to do the cytotoxicity studies on the photoresin, and this used ATDC5 chondrocyte cells. They are derived from mouse teratocarcinoma cells. This allowed the cells to, Alessandra allowed the cells to attach to the flask for 24 hours before testing them with our cross-linker and the photoinitiator system, the monomer with the photoinitiator system on its own, and the two various resins that we developed. As you can see, they're all above the control and the PBS after 24 hours, which is a good sign, as this means we can go to the next step in our work for this and print directly using the green DLP. So summary about our current work. The first series of green light photoresins for AM have been developed, tested, optimized for high resolution. The 3D printed material properties have been extensively characterized. So in terms of CAD designs, a series of parametric design models prepared and tested with the g-DLP. Taking the results from there, the resolution optimization results were integrated back into the designs so that we ensure no failures in the design and that we have the exact measurements and resolutions that are printable in our designs. Models with varying surface area to volume ratios have also been prepared, and that goes to the next part of the work. And importantly, the biocompatibility of the materials has been studied. Cytotoxicity studies are continuously being done on the different resins, and these are currently using mammalian cells. And it's, as we've seen previously, it's looking positive. So the experimental design for the current work with the algae, the first thing we will be doing is testing the algae, the clammy algae, which is Chlamydomonas Reinhardtii. I'm sorry, I can't pronounce that very well. In tap media at varying concentrations versus varying light duration. So here you can see we're going to have 1% of algae at 30 seconds to 90 seconds, 5% all the way up to 20%, and 90 seconds. And then we're going to repeat that for an hour, 2, 4, and 8, which can be the entire durations of the print. And then we're going to study to see whether prolonged exposure to green light will have any effect. Does this impact the algae? Does it stop growing? Do they survive? The next step, once that's complete, will be repeating the exact same study, but for the monomers, the cross-linkers, the photoinitiators, the cross-linkers, and other additives for the exact same time periods to find out the exact working windows for our photoresins. Once we find all the safe concentrations in the working windows, then we can produce the first batch of an algae-infused green light photoresin. So once that happens, as I said, optimize photoresins and algae and tap media, we get our photoresin, and we're going to aim to 3D print using the optimized data from the previous studies, and hopefully get an algae-infused 3D printed structure. So we're going to look to test printability of the simple structures, such as solids, move on to test the printability of lattice structures and more complex structures at higher resolutions. Then we're going to visualize prints under a microscope, test the viability of algae remaining in the media. So obviously after the print is complete, we want to see, has the algae in the media become Is the viability reduced? Are they still okay? And that will give us an indication of what's happening in the print, which will be left in tap media and also tested. So when I say tested, there are several different biological analyses that we're going to undertake. One of them being an optical microscopy inspection of living algae in the photoresin. Another one will be to place the prints in green fluorescent probe cytotoxic screen in a rich tap media. This will stain the cells and allow us to look at whether they're alive or not. But also, live cells will be visualized using red autofluorescence of chlorophyll. So the chlorophyll content will actually be studied at certain time points to quantify the yield and cell viability. The algae will be recovered from the prints where possible. Chlorophyll extracted by cell lysis will determine the chlorophyll content. And finally, O2 concentrations from the prints will also be studied from photoautotrophic growth. And that will give us some information about the photosynthetic rates, which will be very important to go back and redesign the lattice structures or the solid structures. And that's where the comparisons will come in, whether a more complex connected structure has an impact on these rates or not. So the expected outcomes from the study are, for the 3D printing aspect, we want to have a series of biocompatible green algae photoresins, an optimized print parameter setup per photoresin, high resolution prints with complex architectures, and obviously, ultimately, a proof of concept using the green light. Post-printing, pilot results will give us photosynthetic rates, the viability for the algae. Optimized incubation conditions post-print are very important, so we'll be developing that as the project goes. And of course, develop and expand methodology for the analysis of algae gels, which is hard to come by. If you research into it, there isn't that much, and not much at all when it comes to such 3D printed structures at a complex level. And finally, the novelty ultimately provide proof of concept showcasing high potential for green light in ultra high resolution bioprinting. A bit of a summary. So the first ever g-DLP has been created. As you can see there, it looks like a basic printer, but it's a very powerful machine with novel formulations and successful prints. The preliminary studies show that the photoresins are non-toxic with mammalian cells, and they're ready for in-situ printing. So we've got algae and the cells on their own ready for printing. The microalgae viability tests are underway with single resin components. Algae-infused photoresins, first of its kind to be created for the g-DLP, and finally survival, growth, and photosynthetic rates to be studied through various prints. And the future work, finally, the algae-infused 3D prints. So we're looking to test the longevity and the long-term survival of growth of algae in printed gels. We also want to optimize the geometry to enhance the mass transport and diffusion of nutrients/gases. g-DLP expansion. So there is talk of multi-vat systems for layered multi-cell types. So a lot of the bioprinting technologies that you'll come across will actually just have a single cell type. The ones that do have multi-cell types might have them in a very basic structure where you have to change the nozzle or a multi-nozzle type print. Whereas here we can have a much more accurate print technology. And of course, to conduct an LCA, which is a life cycle analysis on the printed algae gels under various applications, as mentioned, pharmaceuticals, bio-waste, etc. And finally, mammalian and bacterial cell work in situ bioprinting. So as we said, we want to create a library of cell-infused photoresins and test for viability, proliferation, growth within the gels, and investigate in vivo bioprinting, perhaps in the future for dental applications, prosthetics, implants, tissue engineering. As the green light is less toxic, this opens the door for much more advanced printing technologies that can be done directly into the body. First of all, I want to thank everyone for listening. And also I want to thank the Advanced Manufacturing Group. Here's everyone, and Dr. Laura Barter and her postdoc, Dr. Einol Zolkepli and Mr. Thomas Wells, Photocentric, IMSE for giving us the opportunity to carry out this proof of concept and move it forward. And again, thank you everyone for listening. And any questions?
Thank you so much. We've actually got quite a few questions in the Q&A section, so I'll get started. So there's a more general question here, and it asks, what do you think will be the biggest challenge for this project?
I think the biggest challenge is translating the resins that we use in UV-based systems, so the regular DLPs and the SLAs, into a green light system, because the chemistry is very, well, I wouldn't say very different, but the system is different in the sense that we want them to be non-toxic to the cells. So we're doing everything in situ. So that's going to be a little bit different. We want to ensure that the process before the print is not toxic. So I think that's quite a challenge, finding the right chemistries, the right concentrations, ensuring that the photoinitiator system is not toxic, as it's a 3-part photoinitiator. I think that's probably the first difficult challenge. The second one would probably be ensuring the mechanical properties are suitable for the gels. A lot of the gels that we've printed with the green DLP have been quite stiff, but also we've had some that are quite soft. And depending on your application, you're going to have to make sure that your gels are suitable to the cell type. So that's quite a challenge.
So we have another question. How biocompatible are the acrylate monomer-based resins?
That's a good question. Some are biocompatible, some aren't. You have to, so I kept it there as a very vague statement, because obviously acrylate-based monomers can range from urethanes, from acrylic acid-based or alginate-based or agar acrylate. So you can have different acrylate end groups that are attached to biocompatible monomers. So it's quite a wide range. So you can have some that are toxic, some that are non-toxic. You just have to start with the basis that you assume is non-toxic, and then you'll have to do the studies on them. Normally what happens is the polymer is non-toxic, but the monomer is. So there's a challenge there.
So we have another question, which actually links into another one, so I'll combine them. So how would you massify this kind of technology, so translate it into a wider scale? And what do you expect about the cost? And what are the main applications that this type of printer could make?
Okay, can you repeat the first question? Sorry, I was sorry.
So it's a two-parter. So how would you kind of translate this technology into the wider scale? And what do you expect the costs would be?
Okay, so I'll start with the second question. So the costs are actually very cheap, in the sense that we've taken a cheap technology, which is the DLP LCD, and we've taken that in particular because it's scalable. Obviously, we have limitations in scalability, as I mentioned, with the resolution, but as technology improves and LCD screens improve, that will also improve. But essentially, it is scalable. It's definitely a cheap option for scalability, or cheaper at least at the time being. Yeah, and sorry, I've forgotten the first question again. Well, I went straight to the first part of that.
And so how do you think this you could translate this type of technology into a wider scale?
I think once people catch up with this work that we're doing, I think different industries will start looking into it. As I said, it can go into pharmaceuticals, bio-wastes, aerospace engineering. It can really have in vitro and in vivo applications. So I think at the time being, it's a very, very early stage, and I think the only way it'll scale up and become more popular is if others take a hold of it and push it forward, which is what a lot of 3D printing is about. I think that's the way it'll move forward, I think.
Great. So what was the photo initiating chemistry that you used to enable the green light printing?
So I think many of you would have noticed I didn't mention the chemicals and the photo initiating system. That's because we're considering it to be a little bit proprietary at the moment, or let's say in-house design. we are looking to have a publication out soon, hopefully. Dr. Kalosaka and I are working on it along with Connor and Laura. Once it's out, I think it'll give you all the answers that I probably have not included in this talk.
Fantastic. So there's a final question here, and it's a more of a broad one, which you touched upon. But where do you see this research going in sort of 5 years and beyond?
It's always very difficult to tell, because us and this at this stage, we're looking at it and we're thinking this is the next big thing. We're hoping it is. There's a lot of science saying it's going to be a very successful 3D printing application. It's always very difficult to tell, but it really depends. If this proof of concept shows that we can print with such structures at high resolution, then it might start replacing extrusion printers, which is also what we use on a lot of our different projects. And we're very limited by design. So as you saw earlier, organs and tissues require very high resolution for vascularization, etc. And you need multi-cell components in there. So in 5 to 10 years, I think if people get a hold of the technology and move it forward, perhaps we're going to be looking at printing complex tissues, complex organs with multi-cell components. And I'm hoping that's where it goes. Yeah.
There was just want to say thank you so much. It was such an interesting talk, and it's great to hear how amazingly these funded projects are going. So once again, thank you to Dr. Mohammed for giving the presentation, and we really look forward to seeing where the project goes. Once again, just a reminder that this webinar will be uploaded onto our YouTube channel, and you can find the links to all of this in the chat, and also the link to our Eventbrite page where you can see all of our upcoming events. So thank you very much to Ali for such a fantastic presentation.
Thank you, everyone. Thanks, Leah.